Hello everyone. Today we will be continuing the packaging series by talking about MEMS devices. My name is William Mitchell and I'll be the one sharing this information with you guys today. These are really cool devices that do all sorts of things, so I hope you enjoy learning about them and how they relate to packaging. If you've never heard of MEMS devices, essentially they're tiny systems on the scale of about 20 to 1,000 micrometers that primarily act as sensors for all sorts of applications. The acronym MEMS stands for Micro Electromechanical System, and that's because these devices integrate mechanical components with electronics on the micro scale in one system for any given application. Now the figure on top over here is an SEM image taken of a MEMS gyroscope. Here you can see these fin-like structures that have been released from the substrate so they can freely move. Now these are the mechanical elements that interact with the environment, and then based on how they react will determine the electrical signal that they output, which can then be interpreted as meaningful data. Now MEMS sensors can be designed for a bunch of different applications like sensing motion, temperature, pressure, magnetics, acoustics, photons, and even electrochemistry. And the bottom figure over here shows the logic board of an iPhone 7 Plus, where on this PCB you have the A10, a few other chips and discrete components, and what I really want to highlight is the 6-axis accelerometer and gyroscope, which is actually a MEMS device that's responsible for some of those motion-activated features, such as making a YouTube video landscape when you tilt your phone to the side. And the point of this figure is really just to highlight how common these devices are in technology, and especially technology that we use on a daily basis, all without realizing that they're there. Now, the market for MEMS is huge. Along the same topic as the iPhone 7, the first iPhone that was introduced in 2007 had only 5 sensors, and now the newest iPhone and Galaxy devices that are being made have up to 20 different MEMS-based sensors. And phones aren't the only devices that require these sensors to function. There are all sorts of wearable electronics like fitness bands and smartwatches that include these kinds of sensors as well to sense heart rate and how many steps you take a day. Other markets like entertainment and smart devices use these sensors as well for all kinds of products. And most notably, these MEMS sensors are being used in industrial and automotive applications, because these devices like accelerometers and gyroscopes are incredibly useful in robots and drones, and mainly for stability, but also for monitoring their environment. Other things like cars also use these sensors for health monitoring of the engine, and also just to provide various features to the consumer. And then obviously self-driving cars use these types of sensors in order to allow them to better perceive their environment and make those adjustments that enable those self-driving capabilities. The way MEMS differ from traditional integrated circuits is that they require these physically movable mechanical components in order to function. And for some applications, like a pressure sensor, they have to be very intimately interfaced with their environment. Now, integrated circuits, on the other hand, really only have to design for the physical support, the electrical interconnections, and the heat dissipation of the chip. Now, the process of fabricating an integrated circuit is very different from fabricating a MEMS device, but that's not to say that every MEMS device is the same, because the process of fabricating a MEMS device can also vary drastically depending on the application. And though all of these processes are very different in their end goal, the techniques used to manufacture them are generally the same. You still have your basic semiconductor processing steps like doping, patterning, etching, and connecting, but you're fabricating a completely different type of device when you're making a MEMS device. Now the top figure here illustrates the fabrication process for a MEMS gyroscope, as we mentioned previously, with this bottom figure being that same SEM image of the gyroscopic structure. You can see you still have to dope the substrate, pattern the features, and etch the mechanical structures free, but this device structure is very different compared to an integrated circuit where you're patterning transistors onto a wafer and building a device layer by layer. And the main differences between MEMS and integrated circuits is the packaging techniques that are used. When packaging a MEMS device, it's very common for a capping wafer to be bonded over the device in order to keep it protected from the dicing, handling, and release processes. Shown here is a MEMS device with a cap wafer that's also bonded onto a CMOS wafer. Now, the cap allows for this empty space, and it also protects the fragile structure below. It can also be used to seal in a vacuum around the mechanical elements of the device. And this capping can be done using various bonding technologies depending on the materials that are being used. Glass frit is the most common and versatile because it just involves wetting the surface with a liquid glass that acts as an adhesive, which when it solidifies is very mechanically strong. This can be thought of as simply just like glue. Anodic bonding is used when the device requires interaction with the environment to function. So again, like a pressure sensor. And this technique bonds silicon to glass without an intermediate layer, like the liquid glass that's used in glass frit. And then finally, metallic bonding allows for smaller bond frames compared to those other methods. So it's used to fit more devices onto a single wafer and to achieve a greater throughput. And overall, wafer-level capping can add to the fabrication costs up front, but it can reduce the overall costs of manufacturing by reducing the costs related to testing each device and also by increasing yield by protecting the fragile components. Now, to attach these MEMS devices to CMOS wafers, kind of as shown in the diagram in the previous slide, there are two main methods. One way this can be done is through wafer-to-wafer bonding, where the MEMS devices are bonded to the CMOS chips prior to dicing. And this method has some benefits like better alignment, smaller pitch, reduced cost, but it also has a lot of drawbacks. And one of the main issues is the difference in wafer size between MEMS and integrated circuits. Because most MEMS devices are fabricated on 6-inch wafers, while other devices are fabricated on 12-inch wafers, which, as you could imagine, can introduce a lot of issues. Now, another issue with wafer-to-wafer bonding is the difference in yield rates. Because MEMS devices often have lower yield rates compared to integrated circuits, that makes your limiting factor how well you can fabricate those MEMS devices. Now, a big solution to these problems, although it adds increased cost, is chip-to-wafer bonding. Now, this is where the MEMS devices are fabricated and diced before ever being attached to the CMOS wafer. This allows you to individually test every MEMS device before you initiate bonding, as well as giving you more freedom to bond to the CMOS wafer because the size difference is effectively irrelevant. Now, that's not the only way to heterogeneously integrate MEMS with CMOS devices. Since there are all kinds of MEMS sensors that operate with a multitude of different working principles, there are also many different approaches to achieving this integration. One method that's shown here is called monolithic integration, where you have both your CMOS devices and your MEMS devices on the same substrate, but with their own designated areas. And this can introduce a few challenges. Since the processing steps for CMOS and MEMS are not always compatible, you could end up damaging your CMOS components with the processing steps that you have to use for MEMS. Now, that can be avoided by first fabricating the MEMS and then using a sacrificial oxide to protect them from the CMOS processing steps, but this adds a lot of cost and it can't always be done. Now, another issue is that sometimes the materials are incompatible, and the materials you want to use for your MEMS devices aren't allowed in CMOS fabs. And then one final issue is that you can't use the known good die approach that was mentioned earlier with chip-to-wafer bonding, meaning that you can't test your MEMS devices to make sure they aren't defective before integrating them with the CMOS devices. Another approach for advanced packaging is using a multi-chip module, or a system in package, which allows you to combine several different MEMS or CMOS devices into a single package. Now, with this approach, you can place chips next to each other, or you can stack them on top of each other using the flip chip bonding method to bond them to the substrate. And this allows an interposer layer to also be used. Now, if an application requires multiple different sensors in the same package, something such as an iPhone, this technique provides that solution. And again, here is shown the logic board for an iPhone that combines both an accelerometer and a gyroscope in the same package. And plenty of other applications, such as navigation, require multiple sensors like a gyroscope, an accelerometer, and a pressure sensor in order to fully function. If they could only use one MEMS sensor, they wouldn't be able to properly do their job. But with every method, there are a few downsides to this. A big drawback is that this requires larger package sizes, which can increase the overall size of the device. And this is pretty bad because the CMOS industry is always pushing towards miniaturization. Now, another drawback is that if you're stacking these devices and their working principle is based off of capacitance, you can experience some signal loss. And as always, with advanced packaging comes the option of three-dimensional interconnects. And just like how traditional integrated circuits experience reduced footprints and improved performance, MEMS devices can also experience these benefits from this method. Since most MEMS applications require integration with an application-specific integrated circuit, something like a processor, logic, or memory, through-silicon vias and silicon interposer technologies are necessary to improve their functionality. TSV technology can allow for direct contact with the MEMS devices inside a package without the use of buried or feed-through conductors on the surface of the die, which can be seen in this diagram on the left over here. Now, the use of these TSVs can also reduce the size of that package by nearly 20%, allowing for more miniaturization of these devices. With any kind of device making, there are always endless challenges that make fabrication difficult. If you don't use a capping wafer to protect the MEMS device, the process of dicing can generate a bunch of silicon and diamond particles that can contaminate or destroy your device, pretty much ruining your yield. And if you do any etching on the substrate, you typically use a rinse solution to clean the wafer afterwards. But since the mechanical components of MEMS are so tiny and there's so many small nooks and crannies, when you evaporate that rinse solution, sometimes the capillary forces can actually cause damage to features of the device, and that's a process called striction. Another issue is when you're bonding that cap wafer over the MEMS, it requires this high temperature bonding, which can sometimes exceed the thermal budget of other components that you have on the device, causing more damage. But the main challenge with advanced packaging of MEMS is the realization of those TSVs. Now, since they rely on deep reactive ion etching, meaning these channels are very long and narrow, as shown in this diagram on the bottom left, sometimes you have to compromise between the minimum hole diameter and the maximum depth. Now, a typical MEMS substrate has the thickness of about 300 micrometers, and that's in order to meet very specific mass, volume, and thickness requirements that are put in place to ensure the strength, stability, and reliability of the device. As a result of that, you don't really have much freedom to adjust the depth of the substrate, so you really have to compromise with the interconnect pitch, meaning you often have to increase the interconnect pitch. Now, this can increase the size of devices, but since MEMS don't have as many connections as integrated circuits, it's not always a huge issue. But an issue can arise in having a misalignment of interconnections between the MEMS devices and its CMOS counterpart if they're not the same size. Now, shown here is an example of a real 3-axis accelerometer MEMS device. Now, the working principle for this device is capacitance, So acceleration is sensed in terms of a capacitance change. And the equation for a capacitance, it depends on the overlapping area of two plates, as well as the distance between these two plates. And this device uses both of those variables, but varying the distance often has a greater sensitivity. Now the left side here senses acceleration in the z-axis, making use of the varying overlap differential. And the way it does this is by allowing the proof mass in the middle to freely move when an acceleration is applied. And this will change the amount of overlap that it has with the fixed comb fingers. Now the capacitance can be calibrated, and then any change in the capacitance can give an indication as to how much acceleration is being applied. Now the right side is an accelerometer for the lateral axes. The proof mass here will vary its distance with the stationary electrodes side to side as acceleration is applied. And with these two accelerometers working together, all three axes can be measured by a single die. Now, the operations and response of this type of accelerometer are mainly dictated by the effective mass and the stiffness constant of the proof mass. So mainly those mechanical components and properties. And finally, the benefits of a MEMS-based accelerometer are that you have lower power dissipation, lower fabrication costs, and they're very feasibly integrated with CMOS devices. Here we have another example of a MEMS-based sensor, and this time it's a pressure sensor, where the working principle is piezoresistivity. Whenever a pressure is applied to the silicon diaphragm, these diffused piezoresistors can react to that applied stress by generating an electrical signal, and this is known as the piezoresistive effect. Now, the vacuum cavity shown here is present for the purpose of allowing this diaphragm to freely bend, as well as providing a reference pressure to improve the accuracy of measurements. And this is only one way of fabricating a MEMS-based pressure sensor, and because there are many others that use capacitive, optical, resonant, or piezoelectric working principles in order for them to function. After talking about MEMS, you may have wondered, well, can we go smaller? And the answer to that question is yes. With the development of micro devices, it's only natural that the industry proceeds to miniaturize technology, and we're seeing the development of nano-electromechanical systems, also known as NEMS. These systems are very similar, except they're on the scale of below 100 nanometers. So the fundamental theories that they operate on include quantum theory and nano-electromechanics instead of classical mechanics. Now, these NEMS devices measure nearly infinitesimal displacements and forces on the molecular scale, and can achieve sensitivity down to the attogram or the attonewton, which is 10 to the negative 18. That's insane. And though these devices aren't perfect yet, they're still in the initial stage of development, and currently they have no real commercial impact. But they make use of the existing fabrication techniques that we see for integrated circuits and MEMS. But since they're on the nanoscale, they face a lot more challenges related to fabrication and packaging, as well as other challenges that may arise depending on the application they're used in. Some techniques that have been used for MEMS, like planar processing, which was derived from integrated circuit processing, imposes these geometric restrictions, making nanoscale features very difficult to attain. Now, packaging is also an issue for NEMS, as it is for MEMS, mainly due to this lack of standardization in the industry, but also because it's so much smaller. So from this presentation, I hope you guys developed a strong understanding of what MEMS sensors are, how they're being used in a variety of applications, and how they're packaged. They're really important devices for the future of electronics because they're being used in automotive, handheld, consumer, aerospace, and medical applications. But they also face a lot of challenges with fabrication and packaging that need to be tackled in the future. But with time and further advances in the world of material science, These devices will be even more common and even easier to fabricate alongside CMOS devices. And though there are many types of MEMS sensors, each with their own packaging challenges, I hope you got a basic understanding of what MEMS are if you've never heard of them before. And if you did know about them, I hope you learned something new. I hope you have a great rest of your day, and I'll see you guys in the next video. Take care.